divide this up into two classes. We decided to merge them so that we could expand on a later class in the semester. So here is the other topic, if you will, that we used to break up into class 12, but it's been condensed. And it's section 13.4b. And now we have oblique impacts, whereas the other one was direct impact, where we just had in one dimension these balls hitting each other. But now we can have a scenario. All right, so this is the direct one that's right up above, right? So this first image right here, here's your direct. But what we can have instead, we could have two separate directions that are taking place. And we could even imagine how this would happen, especially when the velocities aren't equal to each other, where the balls are coming in and they're meeting and they're going to separate right here. It's really dependent on what these velocities are going to be, in which direction they're going to go. Those who are good pool players might be able to have some intuition into what the results of these are going to be. But we don't necessarily need to rely on an intuition. We can just piece them apart and see what we have. So what we're going to find, or our main thing, and I alluded to this in the in our bottom line up front, we want to try to draw a line that we'll call N, that's going right through the center of these two particles. Remember that these are still particles, so their size doesn't matter. And we might make it more complicated by having the size. So what we could do is we could have a component that's coming here, and we're going to call that the normal component of the velocity. And the same thing with this. This is the normal component of this velocity right here. And then we can have a separate component, which we'll call the tangential one, right? So the line that's perpendicular to that normal line, that line that's drawn through the particles, the one that's perpendicular to it, that's going to be what we call the tangential direction. And we could break it into tangential components right here. And now when we look at the impulse diagram that's taking place right here, we will see that in the normal direction, we have what is in essence going to be the same thing that we had in the previous thing. This is just a direct central impact in the normal direction. But in the tangential direction, we're going to see that we have a physical interpretation of why this happens right here. We will see that we will continue to have the component right here, and we like to we'll say this right here, and they're using the prime notation there. We could say that this right here is the tangential component, and here is the B's tangential component right here. We'll see that they're going to be equal before and after. So let me write this on my sheet instead right here, right? That we had, so let me get out my pages here so I can read and write down these things the correct way. Right, so here's two problems. I will record those later. What we want to write down for this right here is, first off, we do in the normal direction, we do the conservation of momentum. And we write in the normal direction, and I guess I'm going to use the prime. I really would like to change out from that, so we'll go VA prime, but maybe one of these days I'll change everything, plus MB VB prime, and we have to we will maybe make sure that we're using the correct signs, especially on this side right here, for what direction that they're going. So that's going to be true in the normal direction. In the tangential direction, we will find out that the VA prime is going to be equal to the VA in the tangential direction. Same thing right here. And you go, why? Okay, well, it's kind of almost better to describe this, and I don't necessarily do that. It's almost better to write, well, if you took the ball, right? If you took this, this right here is with both particles involved, and you can see that the entirety of the impulse is in the normal direction. There's no impulse in the tangential direction, and that's because and it's only true if you ignore any friction. If this ball was spinning, and we are ignoring spinning stuff right now because that's really, we consider that the rigid body type of operation. These are particles, so they don't have enough size, they can't spin. But if it could spin and there was this English on there, and these balls weren't entirely smooth, right, then there would be some friction, right? And so now there would be an impulse that be imparted onto there in that direction. Let's say that this one is spinning and this one is not spinning. So as it's spinning on here, this thing would be imparting an impulse onto there, and now this thing would all get messed up. So like if and really in order to see that impulse, we need to separate out the ball. So let's do the individual, let's just do a ball by itself and not the collection of them right here. So just individually right here, we will do a impulse and momentum diagram. So this one right here, he's coming into the right there, right? So now when he meets an impulse, he's getting one right in this direction right here, right? So here's his component in that direction, here's his component in the tangential direction. And then when he's done right here, let's just say we don't quite know, maybe he bounces back this way, but like he's going to continue on in that direction right here. And it's like, well, if we just isolate this in the tangential direction only, so we are only going to look at this because we don't know what this FDT is. We don't know what this impulse is. We were able to get rid of it when we had two particles. When we have a single particle right here, what we're going to have to look at is only look in the tangential direction right here, and you can see there is no impulse right here. So we have to say that MVA tangential, nothing, no impulse, has to equal MVA prime tangential. Masses cancel out of these. That would have been A, by the way, on each of those masses. And you see that the velocity in the tangential direction before has to equal it afterwards. That's only if there is no tangential. There is no impulse in the tangential direction. So what we do now is we isolate these and treat them as like really two different things. The normal direction is just like the two balls just coming to each other. So it's only the only one that matters is the normal components, and then they have a rebound that in the normal direction. So we're able to look at them and see this as just a direct impact in that normal direction. So when we get down to here, we can change now, slightly change our coefficient of restitution to just now be specific to the normal direction. It's supposed to be A prime normal. I didn't write that in very well. I didn't leave enough space for myself. V A normal minus V B normal. So here we got the rel vel in normal der is the negative over the rel vel in the normal der, right? And then maybe an alternative way to write this, we say VA N minus VB N right here. And so when we have this equation right here will be our equation 1, and this one right here will be our equation 2 that we're going to use, and we also maintain these right here. So that with those things we can find all of the velocity components and figure out what the velocity after an impact is going to be. So our general approach is to take the conservation of each particle in the tangential direction, which just means that before is equal to after, right? So that VA1 is equal in the tangential direction is equal to VA2 in the tangential direction, and the same thing is true for particle B. And then we apply conservation of momentum to the system right here. So that's going to be this equation right here, right? So that's but we do it in the normal direction. Apply a coefficient of restitution in the normal direction, and then we combine when we get those velocities after the fact. We combine them together to get a magnitude and a direction, and that direction, make sure we careful that angle is probably going to be in the normal and tangential coordinates. So we're going to need to take a look at those and in the normal and tangential direction to try to figure it. We have to look at that new angle that we get and try to add it to the angle of the orientation of that normal axis. So I want to be aware of that. All right, so I think I have somebody joining right here. So 1 second here. Okay, so yeah, the end. So we want to be careful, and this is we're playing pool right here. And here's Newt Dog and Wormy, and they're shooting a little bit of billiards. So you probably already have some of this intuition about how like a ball is, like especially when you cut a ball, right? When you end up cutting a ball, and as one goes, this one's traveling to this, and what you're going to find is when it does touch right here, right, like right in there, right, we were going to have, this has a component right here, right, but if it was traveling, I didn't draw this very well right here, let's say that it's coming up this direction right here, or coming with a velocity up. I think a better example right here, so we have like this, so I have another student joining, so 1 second, let's see what happens with this. Okay, they apparently I answered their question without having to answer anything. Anyway, it's got a component already that's going to go off in that direction right there. So it will send the ball directly. This one right here, it has no tangential, so its complete motion is going to be along the line of where these contact right here, right? Right, and that's kind of intuitive. Like when you're playing pool, it's like when you want to cut something with the cue ball, you want to hit it like right on the line of the direction that you want to go. So I wish I had known that, because I'm a terrible pool player, but some of you are probably like aces at it.